Okay, I hope that you can hear me, Josh. I don't know if it's true or not, but anyway, sorry about the mix-up. Anyway, there's kind of a combination of things happened this morning. I couldn't make it in. So I just wanted to continue on. Are there any questions on the homework? It's due tomorrow night. I didn't get any emails, so I'm not sure that. I'm wondering if the Tuesday due date is a good idea. We can talk about that maybe on Wednesday. Right. So anyway, I wanted to go through this. So there's an idea that the chain is a Brownian motion or Brownian chain. Right? So in other words, you have for Brownian motion, you have that the average distance that you travel goes with the diffusion coefficient times the time to the power 1. Right. So this is similar to the random coil equation, where you replace time with the molecular weight and the diffusion coefficient replaced with this squared, like the Kuhn step squared. This is called a Kuhn chain. And it would be represented by this kind of stick figure structure. And so this equation was due to, that equation was empirical initially by Brown in like 1850 something, 50 something. So, but then it was derived in 1905 by Einstein in this paper. So this paper by Einstein. Right? So investigation of theory of the Brownian movement. So I want to kind of go through this paper since it becomes like the basis for two things we're going to use. One thing is this is like the origin of this equation, and the other thing is the origin of the Einstein, the Stokes-Einstein equation. Okay, which is that the diffusion coefficient is going to be kT divided by 6 pi times the hydrodynamic radius times the viscosity. Okay, so the hydrodynamic radius, if you have an object like a polymer coil, then you could say, well, I'm going to pull it, so I'm going to get a force, and there's a velocity and a friction coefficient associated with it. There's an equivalent sphere that would give the same force at the same velocity. Right? So Stokes came up with an equation for this friction coefficient, which is a 6 pi times this hydrodynamic radius, which is a radius, and this was written for a sphere. So that's basically the only real equation for talking about what the drag coefficient is. So you talk about any object, it has an equivalent size that will be the equivalent dynamic size for the drag coefficient size, this hydrodynamic size. So that's kind of the idea. So this equation becomes an important equation to do things like dynamic light scattering, where you look at the motion of particles in space and you look at the diffusive motion. So we're going to follow this kind of equation, like the distance they travel goes to the square root of time. And then from that, you get the diffusion coefficient. And what you want to get from that measurement is the size, this hydrodynamic size. It's a equivalent spherical size of an object that has the same drag coefficient. So that becomes an important number to know about. That becomes like a way to quantify polymers. Right? So since we're here, I thought I'd just go through this paper. It's kind of go through the two things that he gets from this paper. First, this equation, the random walk equation, and second, the Einstein-Stokes equation. So the first equation he gets from go back to this. So it gets from a let's call it Taylor series expansion, which is a standard way to talk about how something behaves. So he says he has particles. In our case, these particles are Polymer coils, but they're just particles in general. And say if they start out at some position, then they would diffuse in both directions. And so time only goes in a positive direction, but space goes in a plus and minus direction. So that single spike of materials forms kind of a Gaussian distribution over time. So Gaussian means that distribution function, this P of X, is going to be exponential. And it's going to have, because it's plus and minus are equal, it has to be X squared. And then it's going to be divided by 2 sigma squared. Sigma squared is the variance for a Gaussian distribution. Right? And there's some zero number in the front. Right? And sigma is the standard deviation. Right? So basically that kind of describes diffusion, but it doesn't. So if you so way to use a probability function like that is you integrate it. So if you want to know what's the average X, you go the integral of the probability function times X dx from minus infinity to infinity, and that would, since it's symmetric about 0, that would give you 0. Right? So the second order is the first number that has any meaning to it, because this, you take the negative values and square would be positive. Right? So you do the same thing, except do X squared, P of X dx, right? And that's the thing that you want to get an answer to, this X squared number, and that's going to end up giving you this BT number. Right? So basically, that's how you kind of use a probability function like that. So Gaussian, which is also going to describe the chain, is this the square of the position. So the plus and minus are equal, and you have the standard deviation number. And if you do this integral, you find out this thing equals sigma squared. So the second moment is sigma squared. They're the same thing. And if I integrate that squared function, I'll show you how to do that later. Basically, X squared is sigma squared. Okay, so you could write this X squared here instead of sigma squared. So the second moment of the distribution. Anyway, so if you have this kind of function, so you know that the density of these particles is going to change with X and it's going to change with time. So it's dependent on 2 parameters. Right? So you want to know the functionality of those. So you expand it in the Taylor series, you're going to take the value and then the first derivative for the value. This is in time. So time is linear, so the first derivative. So you see, like, the first derivative drops out for space because it's symmetric. Because the integral of X times the Gaussian times dx is going to have to equal 0. So that term has to drop out in space. But this term doesn't drop out because time only goes in one direction. And so the basis of this random walk equation is that time goes in one direction and space goes in 2 directions. This is in a 2D analysis, can be done in 3D also, but 2D is simpler. So basically you have the density function, and then the Taylor series expansion, the first derivative, and the first derivative would be times some kind of integral. So you have the integral with the probability in time. Basically, just since that's going to have units of time, just call that the relaxation time tau. Okay, so you just kind of take this integral we would have here and just call it tau. And then the higher order terms, since this term has a value, you ignore the higher order terms. So this supposedly would be the largest term in the series. Then, so you do the same thing with space. So this is the time derivative, and you ignore higher order. In space, the Taylor series is going to be like you take the probability of the thing, and the integral from minus infinity to plus infinity, ends up changing the thing. They'll give you like the first element here. So the integral of the normalized mobility function is 1. So this term's 1. So this one's 1 here. That integral is 1 because the integral, they take the full area of this Gaussian, the area is 1 if it's normalized. Right? So that means this P0 has a value that normalizes it. So that integral works out to 1. It's the definition of the P0. So anyway, that integral is 1. That just gives you the density here. The density equals the density. Those two cancel out. Okay, so you just have the first derivative in time. And the second derivative, again, because this thing's symmetric in space, because it goes plus and minus space, then this integral goes to 0 because it's just as much negative as it is positive. So it's, if the particle decides to go left equally as if it goes right, then the integral from minus infinity to plus infinity will have to be 0, regardless of the functional form. The functional form ends up being a Gaussian. Right, so this term is 0. And then you have the second derivative term, which would be the lowest order derivative. And then that one you're going to keep because that has a value. So it's going to have, so in Taylor series, you do the like x squared by 2, then x cubed by 3 factorial, like by 6. So it'd be like 5 factorial. Right? And you have the derivative, that number weighted by the distribution function. Right? So this just becomes a number, some number. Right? So that number you define as the diffusion coefficient. This whole integral you just define as the diffusion coefficient. And then you have this simple equation from its Taylor series expansion. This derivative in time, and then this, it's the second derivative in space. Right, so that's actually fixed second law, right, for diffusion. It ends up being fixed second law. And so that's the first step in this derivative, is to get this kind of defined fixed second law. And then the solution to fixed second law, is this Gaussian function. So you can solve this second order differential equation. This is the solution to it, is this Gaussian function. Okay, so I said the Gaussian function would be exponential minus x squared over 2 sigma squared. And here that the argument of this thing is x squared over 4 times the diffusion coefficient times time. That means that 2 cancels, so that sigma squared is 2 times this diffusion coefficient. So the variance is 2 times the diffusion coefficient for this Brownian motion. Right? So in the variance squared, it said is the same thing as this second moment. That's average of x squared. This is this 2D. Oops, where did I say this? Variance squared is 2dt. There's a t in there. And so basically that is your that's the diffusion equation. Right, so that's just the first. So first equation, just solve Fick's law, and you find out this is going to define Brownian motion. So that's the first part of this paper. It's part A of this theory of diffusion, kind of how he gets that. Right, and then the second part is going to involve applying a field to this particle. So I have this all written out, but I lost the right, the second part involves, so you take the same particles, you apply a field, and the field Einstein chose is gravitational field. So he has this gravity. So the force is mass times acceleration, so it's mg. Right. So and that also so basically there's a gravitational force, and there's also this kT force going on. Right. So you can get the velocity of this thing by 2 different ways. You can get it. You say the field balance with diffusion gives me a velocity, this vg. Right? And the other way you can get the velocity, so is by considering the drag force. Right? So you can talk about the acceleration, this mg. So you can talk about the velocity due to this. Let's see, the field balance between kT and this gravitational velocity, and then you can also talk about the balance between drag and velocity. Okay, and if you solve the velocity in those two ways and then make the two equations equal to each other, then you get this Einstein-Stokes equation. So that's kind of the point of this. That's kind of where the Einstein-Stokes comes from. So basically, the gravitational velocity. So you're going to have the mass times acceleration is going to equal the velocity times this friction coefficient. And the friction coefficient from Stokes' law is 6 pi times the viscosity times this hydrodynamic radius. And that's derived in a separate thing in the basically in the mid-1800s, like 1850. Stokes derived that equation for a sphere. Right. So then if you write that out, you have Vg 6 pi n Rg Rh, and you can solve for this Vg. Is going to be mg over 6 pi viscosity Rh. That's kind of solution one to this thing. Right. And then the other one comes from Fick's first law. Okay, so Fick's first law is that the flux equals the velocity times the density. And that also equals the negative of the diffusion coefficient times a gradient. The gradient in density gives rise to the flux. Right? So the flux is defined as the velocity of the particle, which called Vg times the density. That's also equal to this gradient of the flux. And then the density itself is going to be this Gaussian density profile. Right? It's going to be rho 0 times e to the minus, and then it's a Boltzmann, not Gaussian, it's a Boltzmann density profile. So you have the energy due to the gravity divided by kT. So you have a Boltzmann density profile. So it's going to basically be energy divided by kT gives you the probability of finding something. So the probability equals e to the minus energy over kT. This is Boltzmann idea. This is entropic energy, and then you can just, since you know that gravitational energy is going to be mgh, so you can just plug that into this. So you have the density is rho 0 exponential minus mgh over kT, and then the derivative of density. The derivative of exponential is exponential, but you take the argument, so you're doing with respect to h, so this mg over kt comes out front. So you have negative rho naught mg over kt, and then the same exponential e to the minus mgh over kt. And then rho 0 in this thing is just rho. That's the original rho. You can just say that d rho dh is minus rho 0, minus rho 0, minus, not rho 0, minus mg over kt times rho of h. Because you end up with, when you drive an exponential, you get the same exponential. You're going to get rho out of it. Right? So rho comes out here, and that's this thing. Right, so this you can park in here and equate it to this. And here you have a Vg times rho, so the rho cancels out. So you're going to get the Vg equals mg over kt. Right, so this the negative. Let's see, negative cancels here because originally, oh, you get a negative when you pull that over. So actually, right here, the negative's gone. Right, so because it's a negative exponential, so that negative mg over kt comes out and cancels the other negative. Right, so anyway, so you end up the vg is mg over kt just from Fick's first law, and then we had before. That's kind of number 2. We had before that vg is mg over 6 pi viscosity times rh. You have an mg common to this, then you have kt, and then this vg, somewhere I put the diffusion coefficient here. It's d times rho over h. So there's a d in here. You wrote the h. I plug that in to get here. There's a d here. This should have had a d in it. Right, so anyway, then you can equate these two and get what the diffusion coefficient is. So diffusion, since the mg cancels out, the diffusion coefficient is kt over the 6 pi viscosity RH. And that's the Stokes Einstein equation. All right, so it's kind of maybe better worked out in here. In the end, people just use that equation. So we'll see this equation over and over again. Like when we want to know how a polymer moves, we use that diffusion coefficient. And the other part of this paper that's important is that it's where the first time that this that the equation for Brownian motion or diffusion. So that's the equation of diffusion. So anytime if you plot like position, so you'll see papers over and over again, and they'll plot like position versus time, right? So the 1/2, or it'll be like log position, log time, and then it'll be the slope will be 1/2, or it'll be 1. Right, so if it's 1, it means ballistic motion. If it's 1/2, it means diffusive motion. So always looking for this time dependence, the square root time dependence to get diffusive motion. So diffusive motion's like a touchstone. Like if you say you do a computer simulation and your particles move around, then in the end you have their position versus time. Well, this is the first plot you would do. If this doesn't work out, if you don't get the position goes with the square root of time, then there's something wrong. Then you have a bias in your system. And if you get that the position goes with time to the power 1, that means that the particles are being driven by a field. Right? So you have the bias is like a directional field in that case. Right? So you can understand this 1/2 becomes like a touchstone to tell a reality touchstone for how things behave. Like if you do a simulation or if you have a theory, it should come out to be that this works out. Right. So anyway, 1905. This is kind of a simple, I guess, paper. You know, it's just a mathematical derivation. But you can see Einstein did all quantum mechanics and things. Basically, he also did quite a bit in this fluid dynamics area. And the stuff he did became like seminal to it. And he also figured out that if you have a system of flow where you have like particles in a system, then the viscosity is going to be the solvent viscosity times 1 plus the concentration times the intrinsic viscosity. And for spheres, you figured out that intrinsic viscosity is what is it? I don't remember what the number is. But basically, he calculated this equation. That's called the Einstein equation for flow. And he figured out what the value of that is for spheres. I think it's 2.3. Right. So anyway, he also derived that business, right? So he did quite a bit in colloids, even though his main work was in quantum mechanics. In this 1905 paper, I think it was cited in this Nobel Prize. There's certainly mentioned as one of his major achievements. Anyway, so that's kind of a flavor of some of the stuff. So we can go to look at how this Gaussian thing is applied, right? Just kind of a quick look at this. So basically, this is again the Boltzmann, right? So you have the probability of something is going to be the energy of that thing. So the probability of something, in this case, the something is you have your chain, right? And then it's got some distance between the ends of the chain. That distance is r. So what's the probability that those two things, what's the separation distance? We say like the probability of a Gaussian chain versus r, and you say it's 0, is the maximum. So that most likely the two ends would be, so we do our random walk simulation. It's most likely that the 2 points would land on top of each other. So that's the maximum. Then that the further apart they get, it's less and less likely until you get to a fully extended chain. Right, so you have like thin L minus NL. Those are cutoff points. And in between, it acts like a bell-shaped curve, Gaussian. Right. So the Gaussian, again, is going to, because it's symmetric above 0, the first thing you can look at is the squared term. Negative means it decays. And then it's divided by 2 sigma squared, and we know that that's NL squared. 2 times NL squared. So sigma squared for Gaussian chain is NL squared, because we figured out that if we find R squared, which is the same as sigma squared, if we do that double sum with the 2 R's, Ri, Rj, we find out that that's in R squared. Right, so we know that sigma squared is NL squared for this Gaussian function. And then it's got some prefactor like probability 0. This follows the Gaussian behavior. Right, so it's given here. There's that Gaussian behavior, but also in the same case, we know that this business is being driven by thermal fluctuations, so that we could say that there's an energy function. So the energy of the chain at a size r over kt gives us that same distribution. So we don't know what the energy of the chain is, but we know that it's going to follow this Boltzmann equation. This Boltzmann equation that's of the same form. It's exponential. And it's going to be the energy of the chain at some position r, at some separation distance r, divided by kt is this Boltzmann. So we can say, well, it's a Gaussian distribution. That gives me the probability of the chain, and it's thermally driven. So it's got to follow this Boltzmann. That means these two equations have to be equal to each other. That means the argument of exponentials have to be equal to each other. That means from that comparison, I can get an equation for the energy of a chain. Okay, so I can find out that the energy of a chain, the negatives cancel, is going to be related to kT. So the higher the temperature, the higher the energy of the chain, and it's going to be related to r squared and then NL squared. And if it's 2D, it's 2. If it's 3D, there's a 3 here. So this Gaussian function for 3D, you just put a 3 here. It's like 3 1Ds. So you take the 1Ds and cube. So you just put a 3 in for the power of the exponential. My 3 1Ds would be 1D times 1D times 1D. Probabilities multiply. Take the same exponential, just cube. Right, so we have that the energy of the chain is this function. Right, so that's kind of interesting. So we can talk about what the energy of the chain is. So what's the use of that? Well, if you stretch the chain, right, then you can turn the chain into kind of a spring, right? So this is just a normal spring equation. So say that the force to change in energy. So force times distance is energy, right? So we have energy is force times distance. That means the force on the chain is dE dr. Right? But we have an equation for E, so we can write, then we can just take the derivative of that and find we have 3 kT over NL squared times R. Is this, and R is our X, so this is a spring constant. 3 kT over NL squared for a single chain. So then we can talk about before we talked about if you have this G prime within the homework and G double prime, and you do it as a function of frequency, and then G prime is going up, and this is log log, G prime goes up to the power 2, and G double prime goes up to the power 1. This is flow. When they cross over, G prime plateaus out, and this is called a rubbery plateau. And then it does some other stuff over here, it crosses over again. Basically, within this rubbery plateau, that number is called G naught, the plateau modulus. Right, and at that point, the scenario is that the chains are like hooked together, right? And there's some molecular weight E between the chains, and we talk about that from that plateau modulus, you can get what ME is. We say that ME equals RT over the molecular weight, right, times some constants. So the molecular weight between entanglements, which is the same, it's like the same as this force equation, right? So the modulus would be like the spring constant. So I do force by area, and I do R by R naught, then this becomes strain, and this becomes stress, and then this thing becomes a modulus, right? So basically, 3RT over M E becomes a modulus. This entanglement gives us our entanglement molecular weight. 3RT over G naught gives us the entanglement molecular weight. And it follows directly from just a simple comparison of the Boltzmann energy function with this Gaussian chain function, which gives us the energy for a chain. All right, once you have the energy for the chain, you can get this modulus, this rubber elasticity modulus. This is the basis of rubber elasticity. So what it means is that you have so you're going to make a rubber, and you're going to start with some chains that's got functional groups on the end that can bond. Either you're going to put in sulfur so that they can link together, or you'll have some functional group like OH that can react. And that can react, and two of these can get together and then make water, so they can react to make a SiO Si bond and polydimethylsiloxane. Right, so you have some reactive end groups, or you just put in sulfur and link up the chains. Right, in the end, you're going to have some MC, molecular weight between cross links. Right, so then you can measure the modulus of this thing, and then you're going to find out that the modulus is going to be 3RT over that MC. So you can get the molecular weight between cross links by measuring the mechanical modulus of the chains, assuming that the chains are Gaussian. So you assume everything we assumed here, that it's a Gaussian distribution, so Gaussian chains, and they're following Boltzmann energy equation. And so some assumptions involved in that, but basically that's the normal way to get the molecular weight. So you can also look at the swelling ratio of a rubber and get the molecular weight. So any kind of a gel or rubber, any kind of a soft material, you can figure out the structure of it just by measuring the modulus. And that's kind of the idea of this. And again, in the case of entanglements, the time-dependent modulus, and the time's going to be, the relaxation time is going to be related to 1 over that gamma dot, or 1 over the frequency at that tailover point, or the crossover point in G prime, G double prime, or the tailover point for the log viscosity plot. So 1 over the gamma dot here, or 1 over the frequency here. And that was in the homework this week. That gives you this time where the entanglements can relax, and it's not, it flows beyond that for longer terms. All right, so it's kind of a lot of stuff, but so I tried to show. So Einstein in 1905, before they knew polymers existed, right, was already talking about this kind of math, like the math that you use to talk about polymers, which is basically Gaussian disordered systems, and then how diffusion happens. So Brownian motion became the model for everything that came after. And then, so all this math is just adopted into polymers. And then one of the first things to deal with was what elasticity was. Right? And then this is kind of Paul Flory, another Nobel laureate, that kind of worked out this rubber elasticity business. But it's all based somewhat on the Einstein thing. Right? So anyway, there's more to do with this, with the exponential stuff. So let's see. So immediately, like when you're dealing with this, you want to get moments. You have a Gaussian distribution, and then you want to use that to get moments of a number. Right? So we know the first moment 0, right? Because the integral of a normalized Gaussian distribution, so the average position is going to be 0 because it's symmetric. So we already know the first moment 0, and also this is a function that you can solve because you have exponential of x squared over 2 sigma squared, right? And then times x. So you can, in dx, because the argument here, if you take the argument of the exponential, to call that y, then dy equals minus x over 2 sigma squared dx. Right, so you have x dx here, so you can solve that one. That's the same thing as the integral of exponential, which is exponential. Right, so that equation can be solved. That's the only exponential equation that can be directly solved. You have to have dx, if your argument is y, you have to have dy outside of the exponential in order to solve it. Right, but there's two integrals that we need, but you can't do that with, right? So one of those is this, like you want to get r squared. So our argument out here isn't r, it's r squared. You want to get what's the average r squared? You want to integrate that Gaussian with respect to r squared. So that one can't be solved, right? And the other one is we want to figure out what the normalizing factor is. Like, where do you get this thing from? And that's an integral of just the probability function, because you want to have the probability divided by the probability of 1. This factor has to normalize it to 1. That you get only by integrating just the probability function. So in that case, you don't have like x out front, x isn't there. So that one can't be solved either. So you have this problem that the main equations you need to solve aren't in your normal calculus book. Right, so how do you solve those is a question. So this is due to this guy DiMarzio written this and came up with this stuff. It's really hard to use before. It's not really in any book. So, okay, so basically you want to solve this equation, but the only solution you have is this equation, like integral of x dx, and then the square is in the argument. Maybe you want to solve it without that x being there. So the way DiMarzio explained to do that, you take that equation, you square it in x and y. So you multiply it. So you have two of these functions. One's in terms of x, the other's in terms of y. So it's in actually 2D space. You have this g function squared. Then you have exponential ax, exponential alpha y, dx dy, right? And then you can rewrite that because something to the power times something to the power is something to the power sum. So you can sum the squares. Now then you can convert this back to radial coordinates, right? So this is just g alpha squared, but it's written in Cartesian coordinates, but y squared plus x squared is r squared, right? And then the dx dy becomes r dr and then d theta, the two coordinates for circular geometry. And so there you have your r. You have your r squared and r, and then you can solve that, right? And the solution to that g alpha squared is pi by alpha. That means that the solution to g alpha is the square root of pi by alpha. And remember, alpha is sigma squared, 1 over 2 sigma squared. So the square root of that becomes just sigma, square root of 2 sigma, and then square root of pi. So that solves the first integral. The second integral you need is to get the average square term. right? And the way to get that one is to realize that that the derivative, so the derivative of this function is that function. Okay, so if you take the derivative of if you take the derivative of this squared integral, you get this. So derivative will take the argument out in front. So you had r squared that goes out front, or x squared goes out front. So here, if you take this function, take the derivative of it. The derivative would be like the argument, the exponential, and then the argument would have to come out front. Right? So basically, you get this x squared, x control alpha squared is the derivative of that function. The negative comes out front also. So the negative of the derivative. Right, so you already have a solution to that G alpha. So all you have to do is take a derivative of that with respect to x, and then you can find the solution to this second moment derivative. And what that gives you is the answer. We have the original argument was if alpha is 1 over k squared, and then you end up with this r squared is k squared by 2, and k squared is 2 sigma squared. So r squared ends up being sigma. R squared ends up being sigma squared. So that's kind of how you solve the two integrals you need to solve in order to get this r squared thing. And also to say that r squared is sigma squared. Right. So that's in here. You guys can look at that if you want to. You know, basically, we're going to go through it more than that. I think it's kind of important, but basically, that's how you can actually solve those equations. You find out, like, if you start looking at those carefully, you can't solve any of the equations. So those are the methods that you need to solve those. So then we say that r squared is an r squared because we already had a solution for that in k squared from the idea that you have ri dot rj, the double sum over I and j. These are vectors. So that thing ends up being n r squared, right? N times the absolute value of r squared. We did that last week. The r squared is that thing, is that thing. Right, so any questions on this stuff, or it's kind of awkward right now with it split up like this. So it's basically just some math on that Gaussian and where these things come from. So the next thing is to say that so it's to define this thing in terms of these dimensions, right? So what the dimension of this object is. We already kind of mentioned that, but basically, if you have some object like a disk, right, and then you can say that it's got a radius, then the mass of the disk is going to go with the radius squared. And a disk is a 2D object. So the fractal dimension is 2 for a disk. And you can say, well, if I have a rod, then like the length of the rod, then the mass of the rod goes with the length. So it's a ballistic object. It's a 1D object. So the fractal dimension of the rod is 1. And if you have some 3D object, then the mass goes with the size cubed. And so df equals 3. So those are called regular objects, meaning that there's some kind of object that isn't regular. Yeah. So you take a polymer coil, which is an odd-looking object, and you say that the mass of the coil, so n, right, is going to be r squared over l squared. And so that's 2d. The df equals 2. The same as a disk. Right, so what is this df actually telling you, the dimension of the object? So if you look at say you look at this object and randomly spin it around in space, right? Then you'd have like the mass and then the volume gives you the density. Right, so how then that's volume is going to be the size cubed by the mass, right? And then the mass, we said, is going to be the size to the df, so the density is going to be r to the df minus 3. Right? Because the mass goes with the size to the df, mass goes with r squared, then to the 3. Okay, so that gives you the density of some object is df minus 3. Okay, so that leads to something kind of weird. All right, if the df is 3, it means it has a fixed density in terms of size. Right? In other words, the density of a 3D object, it doesn't matter how big it is. Right? So it's invariant. Right? Right. So it's an intrinsic property. But the density of something that doesn't have a 3-dimension, the dimension has to be less than the spatial dimension 3, so that the df has to be less than 3. So then the density would always decrease with size for any object that isn't 3D. Right? The bigger the disk, if the disk spins around in space to fill space, right, then the density of the disk has to drop as it gets larger. Because if you have a disk the size of the Earth, it's not going to have much density. It's like taking a plane and slicing the Earth and putting all. So the mass of that plane is going to be a lot less than the mass of a big sphere. Right? But if it's a small disk, it's going to be almost the same. Right? So the bigger the disk gets, the lower the density of it, if you think about it spinning around and filling space. Right? So that's what this fractal dimension has to do with the density. So I'm saying that the density of this Gaussian chain, right? If you average it around, and if you average around a disk, they have the same density for the same size, the same end-to-end distance, r. They're going to have the same density. So all this mass fractal dimension has to do with is the density of the object. How dense is it? Right, so the lower this dimension, the more rapidly the density decays with size. So it's an extrinsic parameter. It depends on how big the thing is. Depends on the extent. Right? So it's not invariant. It changes with size. So the density of these kinds of objects change with their size. That's kind of an odd thing, something you're not used to. Right? So then you could say, well, what's the difference between a disk and a chain then? Like if it isn't, the density is going to be the same, then what is actually the difference between the two? So there's several ways to talk about that. One is to apply a field to it. So put an electric current, to put plus and minus and see what the resistance is. So resistance of that's going to be proportional. Unfortunately, resistance is either rho or r. So let's call it RES. Right? It's going to be proportional to the size directly, right? Because your short circuit path through the thing P is going to be one-dimensional. So if it's a regular object, but a Polymer chain isn't a regular object, right? And the resistance is going to be proportional to the molecular weight n. It's going to be proportional to r squared, right? So this P, this path is going to be r squared for this thing. P goes with R1. This is called a minimum path through the object. Minimum path is like, what's the short circuit path through it? In the short circuit, if it's a polymer coil, it has to follow the entire coil, so it has to go with r squared. Right, so this dimension is called the connectivity dimension of the object, C. Right? Or no, this is the minimum dimension. Right, so you can say, well, df is the same, but this minimum dimension is different for the two. For the disk, the minimum dimension is 1. For the coil, minimum dimension is 2. Right. So then you could say, well, there's another dimension to this thing. So you have the fractal dimension is this minimum dimension times what the thing is. So disk should be 2. right? And the chain should be 1 because it's linear. And then disk is 2 because of the 2-dimensional. This C is a connectivity dimension. It tells you what the thing is. So if you take a sheet of, so C would be 2 here, and D min would be 1 because of short circuit, and then DF is 2. And then for a Gaussian chain, it's 2, and it's the opposite way around, right? The minimum dimension is 2, and the connectivity is 1 because it's essentially a linear chain, right? So you can break apart these objects and talk about what they are in terms of dimensions, but the fractal dimension isn't the dimension you need alone, right? You need this other dimension also, one of the other two. And the most likely one is this connectivity because that says what it is. So if you have a if you have a sheet of paper, it's a 2-dimensional object. This equals 2. If your sheet of paper is straight, then D min is 1 and the fractal dimension is 2. If you crumple up the paper, D min can go higher, and then DF could go to 3, right? Depending on, so it could be 1.5 is D min. That would be a totally crumpled sheet of paper. So this D min would decide how crumpled the paper is. And C tells you it's paper. Right? And then the final number you get from that is how the density in space is, right? The fractal dimension. So I'll talk about more about this next time in a little bit. So sorry I messed up getting in. So hopefully it's not that big of a deal. And so Wednesday we'll meet definitely in class. Okay. And have it set up so I'll be recording also. You can kind of watch online if you want. I'm not sure how well it's going to work, but you can try to do that. And then hopefully that's okay. Any questions? Anything? Thanks.